Okay. So I just copied this picture from Wikipedia to understand what does bias and variance means. So these are four different scenarios. You can think of this as like shooting pistol in Olympics or archery, that kind of stuff where you're trying to aim for the center.
Mhm.
And the bottom left is the ideal thing where all your targets, all your attempts are very close to the center and very little variance.
Yes.
So this is like low bias, low variance thing. And then top left is like where all of them are very close to each other, but all of them are off by exact same amount.
Yeah.
So this is like basically you have any systematic problem. Let's say your bow arrow, the bow is slightly bent or something, or the arrow has some defect. That kind of situation where you are systematically getting the things wrong.
Yeah.
So that creates the bias. And the opposite of that is the right bottom thing, where all of the center is good, but the variance is high, like it's all over the place. So that's like you are not a good archer at all. Your accuracy is low. Okay. And then top right is basically having both the problems together. You are off, but also random.
If the bottom left is the best case scenario, out of the two, the high bias or high variance, which one is a better case scenario for us to have?
Yeah, so that depends, right? So in this picture, I would say the bottom right is better because at least most of the points are within the circle. Here, everything is out of the circle.
Right. Right.
But if the variance is very high, then the top left it might be better.
Got it. Okay.
Okay. So in statistics, you try to like combine these two in some manner. The most popular way is to do the bias square plus variance, which is called the mean square error.
Yes.
Okay. And that is the kind of decompositions we will go through. So I have quite a few formulas like that. I wanted to start with this one. So we have a response variable y we are trying to understand, and we are trying to predict that by some function f of x. Okay. So x is your bunch of regressors and some function of that regressor is f of x is my prediction function. Now
Yes.
f can include some parameter, but like that's I'm hiding that for now. Okay. Now this y expectation of y minus f of x whole square. This is my mean square error.
Okay.
So that's called MSE. So I'm taking the error, which is just the difference, squaring it and taking expectation.
Yes.
So that now we can break in terms of a conditional expectation. First, we condition it on value of x, and then we take expectation with respect to x. So just rewriting this as a double expectation.
Okay.
Okay. Now we want to minimize this quantity, MSE.
Yes. Yes. We
Okay.
want
So we want to minimize the error. So now what people do is they think of can I minimize this for every possible value of capital X? So capital X can take multiple different values, and for all of them, I will minimize the inner quantity. Okay.
Okay.
So that is called the point-wise minimization. And if you do that, I am just written the inner thing here, and that again can be broken into two parts. And I am using this expectation of y given x. So I am just writing y minus f of x is y minus the expectation of y given x and expectation of y given x minus f of x.
Okay. Okay.
And then the cross terms cancel out. So you have two sum of squares of expectation. Okay. Now the first part doesn't depend on your choice of f.
The first point does not depend on the choice. Well,
First
because
part, this
it's
thing is
different. Yeah.
like this is independent of the f. So the all we can care about is the second part because that's what depend on f. And you can see if I match this f of x equals expectation of y given x, then this becomes zero. That is the best I can do. Make sense?
Yes.
So
Yes.
capital F is what I have choice over. The other things are out of my control. So I can change, like move, make this f of x equal the expectation of y given x. So then this whole part, the second term will become zero.
Yeah.
Okay.
Okay.
So that's why we will say that in an ideal scenario where we know everything about y and x, joint distribution and everything, my best predictor is expectation of y given x.
Oh.
Okay.
Okay.
Now, this is an ideal scenario where the joint distribution is known and there are no unknown parameters. This is what you should do.
Right. Yes.
So this is more of a theoretical scenario. Now, in a real scenario, we have data. So that's why the next expression you see the capital D comes in. So capital D is given the data that you are given to you. What is the best you can say about it?
Mm,
So our f of x will be something different, and then this difference will contribute to the bias, and the other difference will contribute to the variance.
just to clarify, the D is what the capital D is what's taking place of the capital X then, right? Because we have
Uh,
the actual data point there.
Kind of, but it's basically of a proxy. It's not a real one-to-one replacement because we don't know the true distribution.
Okay.
So data is our like a base knowledge out of it.
Okay. Okay.
Yeah.
Okay.
So then we have this decomposition. So we have the bias part square plus the variance part, and the sigma square part is the inherent noise.
Okay.
Yeah. So this is the three-part decomposition. I think this formula is very similar to what you have.
Yes. That is
Okay.
exactly what I.
Now this sigma square part is basically out of control of your process because that's something that is unrelated to the X. So if I have
Right.
a bunch of regressors, so maybe there is another systematic process or some other source of randomness that is causing the sigma square part at the very end. So this you cannot do much, you can only estimate it. Among the other two parts, we can try to keep one of them low and the other one high and so on. And if you want the bias to be as low as possible, we look into the unbiased estimators. And for example, the linear regression, the least square estimate is an unbiased estimator. So the bias term becomes zero. And then the variance term, you can calculate how much it is. But if you look at other penalized ones like Ridge and Lasso, they introduce some bias, hoping that the variance will go down and overall you will make things better.
Okay.
Okay. And that depends on the scenario. Like there is no general result that Ridge is always better or something like
Got it. Okay, that was going to be my question then too. Okay.
that. We cannot say for sure that Ridge is always going to be better. Like you choose lambda equals 5, Ridge is always going to be better. There's no result like that.
Yeah. Okay.
Okay. Uh, Results along that direction we'll discuss at the end.
Okay.
You can do better than this first.
Oh, okay.
Okay.
Yeah.
So this is the first part. Now, the next question is what kind of functions f are we allowing? Okay.
Okay.
So linear model specifically says your f has to be a linear function. You are not allowed to do anything else.
Right.
So that seems like a very like strong restriction. And suppose we are fitting a linear model, but the true model is like whatever the data is coming from that is not linear. So it
Hmm.
has some non-linearity inside
Yeah.
it.
Yeah.
So that introduces some bias.
But then can't we
Because
just move to a different model where it's like a model?
yes, but how do you know what's the correct one?
Oh,
Maybe
true.
you introduce x square, x cube and stuff, but the actual model has sine of x
Yeah. 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 Yeah.
or e power x or something. Like you
Yes.
never
The
know
function you
what
don't
it
know
exactly.
is the best.
Yeah,
Yeah.
you know the true function. You don't know the true function.
Yes.
There are some experimental design kind of scenarios where you know the true function. There you should actually use it. But in most real world scenarios, you don't know.
Okay.
So we have to assume that we don't know unless we have been given a formula.
Got it.
Okay, so that introduces some bias.
That
Uh,
introduces some bias. Yes.
okay, but what it guarantees is that my prediction function is linear, so it is very smooth. Which means if I'm trying to predict for two different values of x, say x1 and x2, and this x1 and x2 are close to each other, then my prediction will be also close to each other.
Yes.
And this is important for people in any real world business setup. So, like if you are trying to predict something, and if your input changes by a small amount and your output changes by a large amount, people will be skeptical of what you are doing.
That's true.
So if your input is not, why is the output changing? So your model is inherently noisy. That's what people will say about it. Okay.
Okay.
So linear model guarantees that your model is not going to be noisy.
Got it. Got it.
Okay. I wanted to contrast this with the opposite
So do
extreme,
we
which is the K.
never, so do we never then, Sujay, we don't really even try to model things with like sine, quadratic,
Yeah, yeah, we'll do. We'll do all that. But linear model is our first model, so we're studying that in detail.
but then I thought you were saying though that if x changes a little bit, y changes a lot. That's not a good sign though, right? So,
Yeah, so we have to study to what extent nonlinearity is okay with us.
okay,
You
okay.
can introduce nonlinearity, but you have to see like what you are losing and how much you are losing and whether that is happening or not.
Got it.
Okay. Even linear model, as we discussed in the ridge regression setup, if the singular values are small, the variance can be high.
Excuse me. Okay. Wait, sorry. Can you say that again? I missed it.
Even in linear model,
Yeah.
we discussed while doing this. Let me go back to that first. Uh, yeah. So we estimated the variance of beta hat, right?
Yes.
And that has a 1 by d squared term. So if one of the d is very small, like close to 0, then 1 over d squared will be large. So the variance is large. So which in practice means sometimes if you train your data on two different data sets, so like this can happen, right? So if you did some training of your data, you got some data and you trained on that. Next day, you got some slightly different data. Let's say one or two data points got added. Then you have to retrain it. Now, if your model has this problem where the singular values are small, then introducing one or two points might change the model a lot.
Right. Yes. It'll affect them.
And that's not because those points are bad. It's because
There's
your
not.
model has some other problems like this.
Okay.
So it's not the fault of the new point that made results change so much.
Okay.
And that is the motivation behind using a ridge regression kind of thing if you suspect something like this happen.
Got it.
Okay. So this is like what we are gaining out of the linear regression kind of setup, where like after some work along the ridge regression or lasso or something along the lines, we can guarantee that my prediction will be smooth.
Got it. Okay.
So the opposite extreme is k nearest neighbor. Have you heard of this one?
I've heard of it. I'm not sure. Oh, maybe
How
you
it works?
can like predict oh wait, like you're looking at how many neighbors there are around that
Yeah,
point.
yeah. Find some five nearest neighbors. So find 5 points which are closest to this and take their average response, and that is your prediction.
Ah, okay. Got it. Got
So
it.
for around every point, you create a neighborhood around of 5 points or whatever number of points you choose.
Yes.
Okay. Now, these have two advantages. One is that you don't need to choose a model. You don't need to know whether it's linear, sinusoidal, exponential, or anything like that. You don't need to specify all those things. So it can work for any dimension, any data, and all that. It doesn't have a dimension problem. And second thing is it is like easy to adapt to new data set and all that thing because like the model is new, model is automatically doing the adaptation for you. You can just change the number of that k parameter and the rest of the work is very easy.
Got it.
So it's also calculation is very easy to understand, very fast and all those things.
Got it.
Okay.
Is
The downside
the
is that it may not be smooth sometimes. So the function that you fitted will be locally stepwise linear. So step function kind of thing. It will
oh,
be flat in some interval and then jump up and then again flat and again jump up. That kind of thing.
okay.
Okay. And I also wanted to show you this
Sorry,
chart which was like,
real quick,
yeah.
Sujay. Is K gonna be like a hyperparameter here where you choose
Yeah,
the
K is a hyperparameter. Again, you have to do some cross validation work to choose it.
cross validation or to choose it? Okay, got
Yeah.
it.
If you choose K to be very small, it will be extremely noisy. And if you choose K to be very high, then it's going to be like very smooth, but you will lose the local features kind of.
Okay,
So all the bumps will basically get flattened out
got it.
and will end up something like a flat distribution.
Okay.
So, so this is the plot we were trying to discuss last time. So in any model, we have some concept of model complexity. So for example, in a linear model, you can introduce more regressor that introduces the model complexity. You can add higher order terms like square and cube of the variables and so on. You can add polynomials. In case of maybe some other models, logistic and all, you can introduce some other parameters and all, and increase the complexity and all. So in general, what happens is if you as you increase the complexity in your trading sample where you are treating the distribution data, your error goes down as you introduce more and more regressors.
Yes, because
The
you're
blue
having
line,
parameters to fit the
yeah,
data.
you are allowing more parameters to fit, so your trading sample will go down. But in your test sample, it will initially go down and then go up.
Hmm,
So the test sample will tell you where exactly to stop,
that sweet spot.
when
Okay.
to stop adding more regressors.
But when you're training, do you just put all of the regressors in there just as a like, hey, let's just and then determine it in the test which ones need to be removed? I guess process one.
Kind of, yes. So there are multiple methods, some of which are slow, some of which are fast and all that. Like you have to consider time consuming things as well. But in general, what you can do is you can add one regressor at a time. So you start with any one regressor and then try to add one more and see if it is improving or not, and so on, and keep going.
Until there's no return on it. Got it.
Yes. Some people use the opposite approach also if the number of regressor is like manageable. You start with everything, try to remove one of them and see if it improves, and so on. Like keep removing as many as you can to see if things improve.
Got it.
So, for example, linear regression, one metric is usually used for R square, which tells you how much of the sum of squares is explained. And every time you add or subtract a regressor, the R square will change, and that can give you track of how much it is. But the problem there is every time you add a regressor, R square will increase by a little bit.
Yes.
So how do you know that improvement is worth or not? So suppose it was initially 70%, I got 72%. Is that 2% worth the additional regressor?
Maybe not. Most likely not.
Yeah, most likely not. But if it's a 15%, then it's probably worth.
Yeah,
If it goes from 70 to 85, then it's probably worth.
got it.
Okay.
And this will
So that,
probably relate back to the bias variance trade-off too, right? Because if we
yes,
add more
exactly.
factors, yeah,
So this is